Okay, we shall go on with the next speaker. He's already here, so please stay. Alem Gebremedhin from Ethiopia. He graduated with the BSc in Plant Sciences from Haramaya University in Ethiopia, and was working in Ethiopia at Ambo University since 2007. Alem will present his work entitled The Effect of Nitrogen Deficiency on Tomato Leaf-Water Relations. Alem, please.
Thank you, everybody. My name is, as you know, Alem Gebremedhin, and my title of my research exercise is The Effect of Drought and Nitrogen Deficiency on Tomato Leaf-Water Relations. This work was done under the supervision of Dr. Moshelion here in the faculty. So as an introduction, everybody is aware of the current global warming, and greenhouse gas emission are the most important climatic factors which are affecting the growth and development of crops. So this global warming is causing drought, crop failure, livestock deaths, food shortage and famine across, especially in developing countries. As a result, drought reduces plant water content and water potential especially, which are the most important things in determining plant-water relation. You know, if the amount of water in the plant is reduced and the water content of the leaf especially is decreased, the general plant growth will be reduced as a result of reduction in gas exchange, reduction in stomatal opening, as well as reduction in photosynthesis. So this is drought, is the main limiting factor in reducing yield and quality of production. So plants didn't stay open for drought effects. They try to avoid these drought effects using different mechanisms. One of those mechanisms is reducing the accumulation, reducing the the osmotic potential by accumulating solids. So you can see in the picture, for example, here the plant undertook osmotic adjustment by reducing the amount, by accumulating solids here in the leaf. This helps in reducing the water potential and osmotic potential of the leaf, and it keeps the flow of water from the soil by reducing the amount of water, the amount of energy or water potential here to continue its growth and development by opening its stomata or by undertaking photosynthesis or other activities. But here, if this condition is not happened, it will going to be wilted. So this is one mechanism to avoid the drought effect. Other mechanism that they use it is the elasticity modulus of the cell wall. Elasticity modulus of the cell wall is a relative change or a relative position change of the cell wall when we expose plants to drought or to stress condition in general. So the value of this E or elastic modulus varies from crop to crop and even varies with conditions. So there are ideas in literature that more rigid cell walls have, it is obvious that they have high E value, and total lower water potential at the end of plasmolysis. That means for a given change in water volume. This is the idea taken from Bowman and Roberts. Again, conversely, more elastic cell walls, that is low E, have lower water potential at the Terger loss point, which is the idea taken from Knapp. So having this information, nitrogen deficiency is also another problem related with the water relation activities of the plant. So it's known that nitrogen deficiency limits growth by limiting cell expansion, cell division, photosynthesis, leaf production, as well as tillering. So it will have effect on modifying the water relation of the plant. The response still varies depending on crop types. For example, in a study by Morgan, he found that osmotic potential of the full target cell in limited nitrogen of wheat plant was found decreased compared to sufficient amount of nitrogen, but opposite results from other scholars were found in corn and tomato. So in order to find solutions for all those problems, we can quantify the amount of water in the plant and determine what is the effect and how can we alleviate this nitrogen deficiency and drought conditions, or how can we modify these conditions. So there are controversial ideas here in determining the amount of water in the plant, either taking water potential and determining the amount of water in the plant and considering it as a better quantifying method, or relative water content. So different scholars have different perspectives here. Having this introduction, we hypothesize that exposing tomato plants to drought and recovery irrigation results change in water relations as well as elastic modulus of the cell wall. And again, under nitrogen deficiency, by assuming full amount of water applied for the plant, several physiological parameters, especially those parameters related with leaf-plant water relation, can be modified. So the general objective of this work is to study the effect of drought and nitrogen deficiency on tomato leaf water relation by specifying to compare the change in leaf water relation under drought and recovery irrigation, as well as comparing the change in leaf water relation under normal nitrogen and deficiency nitrogen nutrition condition. So for the drought experiment, we use M82 cultivar. We plant these plants in 4-liter pots having 40% soil, or filled by 40% soil, 30% coconut and 30% peat. We grow the plants in natural photoparade at natural sunlight in the greenhouse. We adjust the temperature to 35 and 25 day and night respectively, and we feed the plants with full irrigation using automatic irrigation system, and we try to adjust the relative humidity also to about 60 to 70 degrees centigrade, percent. So the first experiment done was normal irrigation experiment, which is done about 40 days after we plant the plants. Then we continue the experiment after 4 days, after we expose them for consecutively 4 days of drought, which is considered as medium drought. And the third experiment was done 1 day after re-irrigation of the plants, which is considered as first recovery irrigation, and the second recovery irrigation was done 8 days after re-irrigation. The second experiment, which is done in the hydroponic solution, is nitrogen deficiency experiment. Here, seedlings were grown using perlite for 21 days. We transplant them to hydroponic solution in normal nitrogen condition. So the solution the pH of the solution were adjusted to about 6 degrees, and we use all the solutions, including micronutrients. Then when we grow those plants for about 15 days in hydroponic solution, then one day before the experiment was done, we exposed the deficiency treatments to deficiency nitrogen condition, still by adjusting the pH. And you can see the amount of nutrients used are in micronutrients, in micromoles, and here in millimoles. So we reduce the amount of nitrogen, especially here. So after that, we try to measure the leaf water potential, which is one of the components of water relation for a leaf. So the experiment is done in the greenhouse. So we cut the leaves, and immediately we measure the water potential of the leaf within a few seconds. We use pressure chamber to measure the leaf water potential. The measurement was done between 6 a.m. up to 2 p.m. of the experiment day. So after we measure the water potential of the leaf, half of the samples were taken to osmotic potential determination, which is we put them in liquid nitrogen, and half were taken to relative water content determination. So we use this machine to determine the water potential of the leaf. As I told you before, half of the samples taken from the water potential measurement was frozen and thawed, as well as they were centrifuged at a speed of 3000 rpm for 30 minutes to extract saps. Temperature were adjusted at 4 degrees centigrade. Then saps concentration were obtained as millimole per kilogram using vapor pressure osmometer. So we adjust the millimole per kilogram by using the formula used by Rambouf to change it to megapascal. Of course, at the end, we measure the pressure potential. I mean, we calculate the pressure potential from water potential and osmotic potential. So we use a machine here to determine the osmotic potential of the leaf. At the end, we try to calculate the relative water content of the leaf. Immediately after we measure the water potential of the leaf, we determine the leaf fresh weight. Then after, we dip the petals of the leaves in 5 millimole calcium chloride at dark room for 7 to 9 hours to get target weight. After we determine target weight, we took them to oven dry for 3 to 4 days in order to get constant weight. So at the end, after we measure the dry weight, we calculate relative water content in percentage, fresh weight minus dry weight over target weight minus dry weight times 100. So all in all, we try to have results first on the normal irrigation, and when you see here, the water potential is in the y-axis and the time of measurement is here. So normally the water potential in the morning were higher, which is about 1.2 or something like that, negative 0.12, and it keeps decreasing until the mid of the day. But in the midday, the water potential stops decreasing. So here, when it stops decreasing, we can imagine that the water potential, which is decreasing of the water potential, and transpiration rate is more or less similar. As a result, it keeps constant. And it is normal that tomato water potential is about 0.7. When we see the osmotic potential of the leaf, it starts about here, 0.7, and it reaches about 0.1 in the midday still. The same trend is followed, and after that it keeps constant as the water potential keeps. And here you can see that the change in osmotic potential were small as compared to water potential. This is a logic reason that water potential can show a great change within a day, but in living cell, in living plant, which got enough amount of water in the daytime, cannot reduce that much in its osmotic potential. That means it cannot undertake such a huge amount of change in osmotic regulation of the plant. When you see the pressure potential here, we calculate the pressure potential from water potential and osmotic potential. So it keeps decreasing constantly. It doesn't stop even at the midday, because this is before the plasmolysis point or threshold point. So normally isohydric plants keep decreasing fast or keep losing fast pressure of their cells until they reach early in the tertiary point. When we see the relative water content of the normal irrigation, here relative water content starts decreasing in the beginning, then at about before 8 o'clock, you can see here, it changes the trend of the rate of the decrease. It starts decreasing fast because maybe the sun starts to rise and the transpiration may be higher at this time. But here the plant starts to adjust itself, the relative water content stops decreasing, or it becomes more or less constant in the after 1 hour. So all in all, if you see, for example, the other parameters, they were declining until the midday, but here it stops declining at about in the morning. So something is happened here because they are different. They are decreasing in different rates. So we try to see the relation between water potential and the relative water content of the leaf. Here the relation is not that much satisfactory because you can see the points are out, and we cannot believe that 87 is not bad, but we cannot believe that the amount of points that we took are small because we are taking averages of different leaves. So I can say that it is not linear from the graphs and from the results. So I try to see the linearity of the water potential and the relative water content of each leaves. I mean each experiment, normal, drought, first recovery and second recovery. Here the relationship is non-linear. Here it was linear until here, I can say, but there is no linearity here because the water potential keeps decreasing. And here, the same condition is happened. It keeps decreasing. In the recovery irrigation, more or less, the relation is good. I can say it is good. So, having this information, we try to develop the Hoffler curve of normal, drought, and recovery irrigation also. This helps us in determining the elastic model of the leaf. So, here in the y-axis, water potential, osmotic potential, and pressure potential here. And in the x-axis, we put relative water content. We found one logic here. The relative water content decreases from 95 or 96 to about 84. It doesn't decrease. While we are exposing the plant to drought, it doesn't decrease in more than 84%. This is the actual logic of isohydric plants. They cut the decreasing in relative water content of the plant after some period of time. So here, this line is the pressure potential line, and this one is the water potential line, and this is osmotic potential line. They follow the same trend until around 10 o'clock. This is 10 o'clock, and after that, there were a large shift in the values of water potential. So we chose that to select this pressure loss point as the first point for determining the elasticity of the cell. So we calculate from here to here for determining the elasticity of the cell wall, from here to here for the medium drought. The whole we take here, the whole we take here, because they are more or less the same. They follow the same trend in the slope of the leaf. So when we are calculating the elasticity model, and when we are comparing the water relations in general as the morning and midday, when you see the water potential, T1 is morning and T2 is midday. So when you see the water potential in the morning, there is no any significant difference for all treatments, for normal, drought, and everything. Here in osmotic potential, there is an osmotic adjustment while we are exposing the plant to drought and recover it at the end of the recovery, that means. In the other parameters, in pressure potential, water potential, there is no any significant difference. Here in the elasticity model, which is our main objective, if the cell wall is rigid, the elasticity value is higher. So the elasticity value is higher. So even though it is not significant difference here, even though it's not significant difference, the values are higher here. So there is something changed in the cell wall of the plant, and this helps us to define that when water potential is decreasing, that's why the relative water content doesn't decrease following the trend. So here you can say that in one experiment we can find only one point here. That's why the errors are showing some noises. But in many experiments we can find many results, and you can imagine that this error will not be happened in this. And if there is elastic modulus here, higher elastic modulus here, there is a change in the cell wall of the plant. Again, with the nitrogen deficiency experiment, we follow the same trend, and we try to determine the water potential difference between the two treatments within the experiment day. So this one is the normal nitrogen condition, and this one is the deficiency nitrogen condition. You can see that there is a significant difference between water potentials of the two treatments in the morning, especially until around 8 o'clock. And when you observe the plants normally, there was a lot of guttation in the normal irrigation one, and there was not that much guttation, I can say, in the deficient one. So this is due to the reason that when there is deficiency in nitrogen, one, there is a resistance from root resistance of the root to water flow. Other thing, it is related with the transpiration rate. My colleague Z found the change in transpiration rate here in our lab. So this change is happened due to the transpiration rate also. There is high transpiration rate than here. Comparing the the osmotic potential of the leaves here in the normal and deficiency irrigation, here there is no any significant difference. You can see the results and the noise of the SE also. I think we didn't repeat this one, of course. That's why there is no, but we cannot say that, we cannot say anything that there is a difference here between the two treatments. They keep the same trend when they are decreasing in the experiment day. Here, when we calculate the pressure potential of the leaf in the normal irrigation, we predict that it must be somewhat higher or somewhat change. And here, it's not significant difference, but the trend is showing. And we can repeat this one also in the next times. Here, in the relative water content comparison, we predict that the relative water content of the normal nitrogen condition is higher as compared to the deficient one. So it follows the same trend. I think the number of observations here are small, so we couldn't find significant difference here, but it follows the same condition, and the normal irrigation shows, even though it is not significant difference, it shows somewhat larger until about the midday. So we try to see the Hoffler curve of the normal and deficiency nitrogen also. So I can say that the nitrogen, I mean the water potential of the normal or the control one keeps decreasing slight in the beginning, and it goes down fast. Here it was the same here as compared to this one, but the trend is shifted. So maybe there were some signals related with hydraulics of the leaf, which helps it to decrease fastly while we are exposing to low nitrogen. The other parameters are more or less the same, so we don't have any such a big difference between the osmotic potential, for example, and the pressure potential. So in conclusion, water potential and osmotic potential attain their lower values at the midday, but not pressure potential. Pressure potential continues decreasing until we end the experiment. Relative water content was decreased at fast rate in early times, but then it keeps steady. Lower osmotic potential was obtained at early hours of the recovery day, which is a significant difference from all. And water potential at normal nitrogen grows plants were higher at early hours of the measurement. Thank you.
Thank you, Alem. Yes, Jana, please.
I want to ask you one thing. You used 40 days old plant in irrigation experiment, no?
Yeah.
So why you selected the 40 days? What is the logic behind it?
Okay. Can I answer? Yeah. We don't have any reason to select, but we have the prediction that the plant reaches at a reasonable condition to respond to the water relations of the environment at that time. The plant grows normally at a good condition and reaches to that level. So at that time, we can predict that the plant is ready to have good information about the water relation of the leaf.
Means it is not ready before 40 days and after 40 days, or
It
what?
will flower after 40 days, so it will have problem on the determining of the water relations.
Before 40 days, what will happen? It will not
Before
respond
40
good?
days, we don't have enough leaves to undertake the experiment. It is small.
Next thing. In elastic modulus that you showed, though statistics is not with you, but you are saying that they are different. How could you say that when statistics doesn't support you? You said there is a difference.
Okay, thank you.
Statistics was not with you.
Okay. Here, if you see the results, for each experiment, when you are determining the slope, you get one value. For example, if you repeat the normal irrigation 3 times, you will have 3 values. If you repeat the drought irrigation, again, we will have 3 values. So when you run them in the jump, I think you will not have significant difference within 3 repetitions. Maybe you are expected to have more than 7, 8. And if you have, I'm sure that it will be significant if you repeat this one many times. Because you can see the noise. It is about 3, 4, something out of 8.
Yeah, but it's not sure. We can have, but we must not be sure without seeing
Of course,
it. So
we
how
can't
could you
predict.
Yeah, we can predict, but we can't be sure, no?
I didn't say sure.
To help your decision.
Did you say there was an isohydric behavior in the?
Isohydric behavior.
Yeah. So would you expect the same behavior if it was an isohydric behavior?
No.
What would be the
If it
difference?
is an isohydric behavior, the plant loses its water content until maybe until it reaches 50–60%. It exposes itself for the stress, so it can reduce the amount of water up to some period of time until it reaches the tertiary loss point. But isohydric plants didn't have such type of characteristics. They allow the water to decrease up to some point, and they stop, they close the stomata.
My question is, you did the deficient irrigation, right? And
Yeah.
it is for the certain days you stop the irrigation or you reduce the amount of irrigation?
It was not irrigation, of course. It was hydroponic solution. So we were changing the hydroponic solution. We were adding solutions to the hydroponic solution day to day. So we were keeping the amount of nutrients to be continued constantly and to feed them properly in the normal
You said your
equation.
one is normal irrigation and next one is deficient irrigation.
One is normal nitrogen solution, and then
No,
the other
she's
one
asking
is.
about the irrigation treatment.
Are you asking about
Yes,
irrigation?
yes.
Oh. We we give them enough amount of water in the beginning, then we expose them for 4 days to drought.
Okay. And next one the graph. I think you have to.
Which one?
It's about the water potential. Here, no, next one. Next one. It's already has gone the down.
Okay. Here? I don't have an
No, it's the 11 EM. You got the higher. It means the water potential is increased in the 11 EM. I just noticed. I just want to curious why that happened. Not in this graph.
Okay.
Not in the beginning. It's near to the middle.
In the beginning, I have here one water potential.
It's the comparison between the next one.
Okay.
Next one. Okay. This one. The 1130 you got the higher pressure potential, and then what is the cause behind that?
Here, this is pressure potential, by the way.
Yes.
Here in the pressure potential, you can see, you cannot say higher here.
No, that's the pattern of curve.
It's not significantly different. So I cannot say higher. It's the same.
Okay, then. But it looks different.
It looks different. There is something noise, and we have to repeat this experiment. We have a plan to repeat it.
Okay, thank you.
Other question? Alem, any conclusions as to what should be done with respect to fertilization when let's say in commercial growth, when water stress naturally occurs here and there?
Here in our
to optimize the response.
To optimize the response, for example, based on our prediction, it is better to, how can I say, we can expose plants to drought and then recover them. As a result, we can improve different production qualities. For example, if the plant have more elasticity in the cell wall, we can have better adaptation and yield, and we can get some advantages over this one to avoid drought.
Mm-hmm.
So we can get this advantage.
So will the advantage of adapting the plants, will it be greater than the disadvantage of exposing it to drought?
We think so. If we adapt the plant, if we expose the plant and becomes adapt the environment, we can solve our problem.
You mean you expose it to, let's say, controlled drought in order to
bring change in the elasticity of the cell wall.
More questions from the audience? No emails? Okay, thank you very much, Alem.
Thank you.